talk about ultrasound principles. So the definition of, I've recorded this 5 times and it's 5 times the same thing. Okay, good. So the definition of ultrasound is any sound wavelengths larger than 20 kilohertz. The sound in general or the human sound, the human ability to hear will be on sounds between 20 hertz and 20 kilohertz. However, those infrasounds listened by a very, very deep sounds like the elephants are not listened by the human ear. And any sound larger than 20 kilohertz is considered ultrasound. The dolphins use ultrasound. Submarines use sonars with ultrasound. In a nutshell, any ultrasound has to be um, transmitted through a liquid or fluid medium. Now, the ultrasound has different applications, either cleaning, like you go on an optical shop, therapeutics, when you go to a physiotherapist and you have deep heat tissue, cutting, you will use, the biggest one would be the phaco machine for us, and diagnosis as the one that we use to evaluate the eye when some other methods are not possible. The excellency of the ultrasound in the eye is due to the fact that it's a cavity filled with fluid and filled with fluid medium that allows the sound to go back and forth. The principle of the ultrasound, or the way that is how the ultrasound is created, is by the most important part. It's called the piezoelectric. Piezoelectric is a crystal that is excited by energy or by electricity, and this current will provide to vibrate a certain way. This emits a scream, a sound, signal that travels all the way to the back of the eye, in this case, and then comes back to the piezoelectric. And the piezoelectric is a female device. I'm sorry for the gender jokes, but it's capable to hear, talk, and listen to the same time. None of you guys is capable to do that, despite what you think you can. You're not. So this piezoelectric is the most important part because it is a movable part, which is sitting at the front of the probe, as you can see here, and it's the one that moves and vibrates every time that is excited. Now, there are several and many different probes and frequencies using the eye. Those are some of the most general. From biometry, from posterior, diagnostic, and anterior, those are pretty much, from 10 to 50 or 8 to 50. Those are the main probes, and those are used with handheld ultrasound. We need to understand how does the image comes alive and how does it work? And the easiest ways to understand an ultrasound is with an A scan. A scan is a biometer. If you have been in the industry long enough, you know that you need to take the length of the eye and measure the internal parts of the eye to see what sort of a IOL you're going to fit. And the IOL on the biometry works with only one probe that is stationary, doesn't move. So it's like an arrow, goes in and out. And this probe, or this ultrasound probe, will generate one line, and that line goes all the way to the back of the eye and then comes back. And every time that this one finds a gate or a change in density, it will produce a peak. That means that this peak is going to be measured in time. So we measure sound, we measure time, we measure in time. We don't measure in distance. It is that time difference that allow us to know exactly where we are, knowing the speed of sound in the different areas of the eye. We're not going to talk about that because we're going to make it too complicated, but the eye will have different speeds around the whole eye, which is more relevant when we're talking about from the back, from the whole eye, and not only on the anterior segment. So that's why I don't want to go into that. When we do a biometry, and bear with me, I know this is boring. When we do a biometry, we will see in the biometry different peaks. The first peak is anterior cornea. The second peak would be a posterior cornea. This is true only if we're doing an immersion scan. And oh, great, this is moving. Now, the third peak will be the anterior surface of the crystalline lens, then the posterior surface of the crystalline lens, the retina, and then the sclera. And this is what we normally see in a scan. Let's not go into there, but basically, the taller the peak is, the taller the amplitude of that peak, the dense is the structure. And the softer or lower the peak is, the softer or less dense will be that. Now, just remember that amplitude. And the way that you see it in an ultrasound is going to be, you have to, in a scan, you will only have one. You will only have one line and you analyze one line, which is a little bit different when we're talking about B scan. B scan is two-dimensional, but there are a lot of different scans, a lot of different images, a lot of different A scans. That means that when you shoot, when you have one line, what you're doing here is that you have one line here, and then now we're doing this, and we have several lines. So we have a lot of lines happening at the same time. Okay, so A scan is only one. That's it. That's it. That it doesn't move. This one will move from one, and then we're going to make a lot of different lines. These different lines, we're talking about brightness. And the reason is that each line, each A scan is going to give you an amplitude. The taller it is, the wider it is, the shorter it is, the blacker it is. So this is a black and white. This is, 256 shades of gray. And in this case, we're going to allow to measure the image based on the grayscale. Now, so what it does is every time it finds a peak, it's going to give you a white image. Sadly, that square is wrong because it's showing you a black image, which it shouldn't, or a black dot. The taller the scale is going to give you a really tall peak, and that in that instance will be a white, or if it's none, it will be black. And this is, imagine now we put here, 3,000, 4,000. There is a lot of different points. 2048, according to some technicians, I believe there is more than that. I believe there is way more than that. And those images will give you, those amount of points will give you that. So that, what this is, it's a bunch of lines, A scans, put it all together to give you that image, okay? And that's why it's called B. And B scan is for brightness. That means the brighter, wider, or the not so bright, the less white it is. So, and then it works on 256 gray scales. It's more than 50 shades of gray. We have 256. Now, so remember that when we're talking about A scan, we only have one scan going back and forth. It is a 10 megahertz scan, so it has a lot of penetration. And a B scan, it will have a different penetration. In our case, is 50, and it's two-dimensional. So this moving, you have a movable part. On A scan, stationary. On B scans, you have movable, and you have a lot of different scans. And so if someone asks you why our scan cannot measure the biometry, cannot do the biometry, well, there's two different answers. First, it's we need a 10 megahertz probe to see the back of the eye. We don't have a 10 megahertz, we have a 50 megahertz. And second is the stationary probe that measures amplitude. And we have a movable probe that we're measuring brightness. And that's why it's A scan versus B scan. You need to remember that, because every time you do a presentation, you talk to a doctor, they're thinking why I cannot do this and use it as the IOL master or whatever other unit I have. There are some technical concepts you need to know. And these technical concepts are basically the amplitude. And it's basically what is the height? What is the height of the peak? What is the height of the wavelength? What is the height of the sound wave? And the higher the amplitude, the stronger is the echo. The lower the amplitude, the smaller is the echo. And that's why we measure the amplitude on the A scan. So when you scanning the sclera in the eye, in the inside 100, you have a lot of white. That amplitude is really, really tall. But when you see the anterior chamber, it's black because there is no reflectivity. There is no echogenicity. So there is the echogenicity of the vitreous of the aqueous, sorry, is zero. It doesn't bounce back. If there is echogenicity in the vitreous, there is probably an infection, there will be blood, there will be pus, there will be something there. So the amplitude is how bright it is, how much reflection a tissue will give you. Now, the gain, imagine for those like Steve Holland, that is a music band, this is the gain is the volume. It is how much volume or how much power are we giving to that piezoelectric to produce a sound wave. It is normally in many in regular standard ultrasounds, you have a pot, and you're going to have a knob. This knob is going to give you more or less power, and this more or less power is going to give you more or less gain. Ours is optimized, and we always are reading to the optimized levels. You can modify the gain on the settings. The more gain, the more wider it will be, the more bright it's going to be. You can overexpose an image. The less gain is going to be, less wide is going to be, a darker, dull image. Okay. Now, the wavelength is basically the difference or the distance between one crest and the other one when you're doing the cycles. We're working on 50 megahertz. That means that we do 50,000 cycles per second. So that's what is called 50 megahertz. So we're doing 50,000 cycles per second. And this is the amount of stress we're going to see that. Okay. Sorry, that was frequency. We do 50 second megahertz cycles per cycle. The wavelengths will be measured by the distance between crest and crest. Okay, so both of them are related. Now, very important to know that when we're talking about megahertz, this is not like megapixels. It's they are some analogies, but not all of them work. The higher we have, the higher the frequency, the higher the resolution. So we have a one-to-one relationship with the megapixels. The higher the frequency, the higher the resolution. However, the higher the frequency, the lesser the penetration. So if you have a really high frequency, let's say like 80 megahertz, you're going to have a really shallow penetration. That means you probably will only go to the cornea, or you would not go anywhere near probably around a few millimeters into the sclera. We're using 50 megahertz, and with 50 megahertz, we have an optimal frequency to, and I know there says 40, but when we use 50 megahertz, we can see the back of the eye, the back of the capsule, the back of the crystalline lens, and we can see the cornea with really good resolution. Nothing behind the posterior capsule. It's very hard to see anything here, okay? But we will be able to see this area really, really good. So this is the green square. When you look to the back of the eye, you need a lesser resolution here. So remember, high resolution, less penetration, high resolution, high megahertz, high resolution. Now, what we call resolution is the ability for an ultrasound image or is the ability to differentiate two different structures. So I'll give you an example. When we talk about that the ultrasound has 3 to 5 microns resolution in the back of the eye, is that if you put there a 4 micron disease, they're going to be able to see it. But if you put a 2, they won't. So the maximum resolution is the minimum objects that you can see or you can detect. In the case of an OCT is between 3 and 5. In the case of our device, we are working with a really good resolution in the anterior surface. There are claims that we can do up to 1 micron change in the epithelium, and we can see usually the 50 megahertz will produce a resolution of around 30 to 35 micron structure. And but that's something that we need to check with the technical guys. But basically, is the resolution is the amount of precision or the minimum distinguishly structure that we can see. Now, there are some factors that will alter or will influence the quality of the scan and the quality of the image. That means that, give me 1 second, because I have here, okay. So this is what it's doing here. We are, the main thing is the angle of incidence. So in order to produce a really good image, we need to be perpendicular. An image taken on the side or taken at an angle, it will produce a alter or a dodgy scan. We need to be perpendicular to the area that we are analyzing. And the reason is because this is sound that goes in and goes out, this sound, you need to address it, you need to confront it straight away. So you have to be direct. You have to be perpendicular. So the reflection you're sending is the reflection you're getting. If I do this, that will go that way, and some of that will come my way, but not all of them. So you need to be perpendicular. So the angle of incidence is really, really good. The more perpendicular, the more angle you are, the lesser is going to be that structure is going to appear to be a little bit smaller. Another thing that affects the readings is when you have a polymorphic surface or a different surface. So small surface will give you a really nice beam. A flat surface is going to give you a nice beam. But those surfaces that they look like Cheetos is going to look a little bit different. Now think on how clear the cornea is. We can see it. Think how clear we can see usually the iris, but when we see a cyst, the cyst looks a little bit weird, and that's where things gets a little bit confused. But so we need to recognize that some structures are going to give a different resolution or a different perception. The sound beam, every single probe has a focus area. This focus is pretty much where the maximum resolution of the beam is created. So the maximum, it's where we can get the maximum resolution, the better visualization, where we should be mindfully placing the focus on the area that we're going to evaluate. This is true for A scans, this is true for B scans, this is true for the inside. And we place that red line that shows where the focus is and where we should be focusing. It's a doctor will tell you, why I cannot see the cornea well and I can see this much better. I want to see everything perfect. This is not an OCT. On an OCT, because an interferometer is going to show you all those images really, really clear. We don't do that because our our capabilities is only just to focus on one area only, and we focus the area of study. Looking at the cornea, when we are focusing to do an ICL, it's a waste of talent, waste of time, and a waste of focus. So that's why you're going to see, I don't know if you saw it today already, or last week, you're going to see the Scout scan that is going to allow you to quickly position the focus of the image in a much better position. You have to notice also, and you saw here, that normally these structures are way brighter than the structures on the back. And this is true based on the attenuation. The deeper we go into the eye or into any tissue, there is going to be um, a loss of volume, a loss of power in that sound wave. This is the same to have the potty in your living room or 3 or 4 houses next to you. That means the sound will lose their effectiveness. And we want to keep those ones, and we need to work with that. And how do we do that? We do that with something called time gain control. Our device already has the time gain control, and it will allow you to show the image on like is happening at the same time. So just to explain you in a little bit way, when you have the sound traveling from the cornea, then to the iris, and then to the posterior back surface, and then comes back, the way that the eye is presented is going to be depending on what time you decide to see it. Are you going to see it on the time that hit on the cornea, or the time that hit on the retina? There is something called time gain control that shows you the image already put it together in their maximum peaks, all of them at the same time. And that's why you get something like this. This is a time gain control. And yes, it always will look a little bit deeper or sadder or darker on the back of the eye, but that's normal. But it tries to give you the maximum image that was acquired in every single instance of this area of the eye. Another thing that is that we need to be careful, especially with the membrane, is the artifacts. Artifacts are shadows or things that they're not there, so they are illusions of of the ultrasound, that they are shadows that appears from an object in front of the area of study. That means in this case you will have this case is okay. So this is that's a worm, but this bubble here is going to produce different shadows on the back. And when you have an IOL, it will be a shadow in the back. When you have the membrane, it's going to be a shadow on the back. If you have a dislocated IOL, it will give you shadows on the back. So everything that is behind, it can produce a shadow. We are constantly fighting against our friends AOCT. Okay, so we are and the reason is the doctor will tell you, oh, but this is a better image. You can see that this is perfectly fine. This is a really, really good image. But what happens there, what happened here, we don't know. So the OCT do not tell you the whole story of what's happening behind the iris. This is very important for ICLs. This is very important when you see in tumors. This is very important when you want to diagnose anything that is happening behind the iris. The OCT is great for retina, and it's great for anterior iris, and it's fantastic for cornea, but not on the back of the iris. You cannot read behind the iris. So not all B scans are the same. Okay, I don't know who the guys are, but those guys are. But I thought it was really cool to find a list of suspects for the presentation. And you have, number 1, number 2, number 3, number 4, number 5. Who are those guys? And you can see that you have Accutome here, you have Sonomate, you have the OCT, you have Quantel, and you have us. When I first saw the R scan and the inside working, my first initial thought is, oh my God, this feels like a primitive OCT. And I'm not saying this to insult anyone. I'm saying this because it is so far advanced than the regular UBMs, that it looks like an OCT with the benefits of a UBM. And this is what we have. And we have, I know that this scan, yes, I know what you're thinking. That R scan image looks better than that OCT, but that's a matter for another discussion. Anyway, now we cannot compare, in reality, we cannot compare a handheld UBM versus the inside. I mean, yes, they both use an interface to fill an area with fluid. They both use a probe, and they're both analyzing the eyes. Well, in the same way that that Spence Tesla, it is like Steve Holden Opel Manta. I know that you cannot compare the coolness of the Opel Manta, but it's not the same car. It is totally two different things. And this is the future. We represent the future. So can we compare it? Well, yes, we're evaluating the eye. Yes, both are ultrasounds. Yes, we try to look at the same, but we sell the unit with the most expert technician inside of the unit. The only thing you have to say is, what scan do you want? With the other one, you have to be the technician. With the handheld, you have to be absolutely everything, and that is, it's quite complex. Now, there are two different ways where the handheld ultrasounds take the image. It could be either on linear or could be just the regular one they do. Now, look at it's interesting to see that the linear image will give you square image. It's going to be here. It's going to give you square image. It's not cut in any way or form. And the regular ultrasounds, this is Sonomed, Accutome, and Helix is gone, so Helix is out of the market. It's going to be a cone. And the reason is that it's a reverse image. So here, the probe will move in this direction. So it's going to move in that direction, back and forward, in parallel to the iris. And this one is going to move this. So what you're doing here is you have like two different circles putting next to each other, and you're trying to scan these in a different direction than the eye is. And that's why the image is never that great. That's why the linear is much better. Now, when you see ours, okay, this is the presentation of the unit. When you see ours, we are scanning all the time parallel to the cornea, and basically the cornea, but also we are trying to maintain that circle or semisphere movement or shape of the eye. That means that in most of the cases, we're going to be perpendicular to the area that we're evaluating. So we move in 5 different axes. We move in, up, down, we move in circles, we move in diagonals, we move back and forward. So, and we are controlled by computers. So we're highly reliable and highly repeatable as long as the orifices are working. Oops, that's okay. That's fine. Now, so we produce images all the time parallel to the area of study. And this is important, and this is the basic, this is why we have a better image. On top of that, we have better sampling. That means that the amount of images we take, each image will have a much more information than a regular UBM image. So we have a higher sampling. That's why we're called high resolution UBM. This high resolution ultrasound that we produce is because of the amount of information we have per scan. And if you see our image is different. It's in this direction, it's not in that direction. So we have this direction of image and this direction because we're moving in an arc scan. We are scanning in an arc, duh. Okay, good. Now, when people talk about reliability and repeatability, if you want to see what's here, give me 1 second. I'm sure you've seen that before, but just in case. There you go. So when we talk about the angle and the sulcus repeatability, the other guys just sucked at it. It's because you are depending, they are depending on a technician. We own the technician. It's called the motors. It's the gamma motor, and it's a belt, and it's a lot of XMLs, thanks to Matsasu and Eric's team. All these guys are producing a lot of different movements, calibrated, micron controlled to produce the same image over and over again. That's why we can reproduce images with 0.2 microns, 0.2 millimeters. So it's 0.12 of the millimeter, of a millimeter. So it's 12 microns. This is fantastic compared to the other guys. Just look, from Opticom, from Quantel, from Sonomed. I mean, though they are bad. And this is in the same hands with really good people. If you add Johnny from the coffee shop that now is working in the ophthalmic industry, and they have to do a scan, it's a much worse story. But anyway, let's not go against Johnny. He makes a good coffee. Now, this is it for now, and I hope you like it. But this is what our ultrasound in a nutshell is, and why that is why we're different. I will see you guys later for questions. Just take notes and